Good morning, everyone. There's a reason the New York Times talked about earthquakes today. Tomorrow is the anniversary of the 1906 San Francisco earthquake, yes. And also there's going to be a release of a scenario called Haywired that's going to be related to some of the things I'll talk about today. So today I'm going to talk about how we use HPC for earthquake research, but also for impacting society with better designs as well. So what is SCEC, the Southern California Earthquake Center? Our mission is to solve problems in earthquake system science, so globally. We want to understand and model the physics of earthquakes. How come I have 13 minutes left? I just started. Can someone reset the timer? That's unfair. Please. I don't want to go over time, but yeah, I just started 25. Oh, okay. That's okay, it's all good. So we want to understand and model the physics of earthquake processes from the tectonic stresses in the earth to that propagating to the faults, creating ruptures and ground motions. We use the Southern California as our natural laboratory, although what we learn and all the technologies we developed are applicable to other places as well. So SCEC is a large collaborative center. We have a multidisciplinary planning committee that develops a yearly spending plan and research plan. We're about at a 10 million a year funding, and we fund diverse projects in geoscience, computer science, earthquake engineering, and so on. And we support both the fundamental science and the applied science. So we have over 1,000 participants. Our annual meeting every year is 600 people. It's a very popular party in Palm Springs every year. We have a bunch of core institutions, so mostly academic, who participate with us. And it's mostly funded by NSF USGS, but we also get funding from Pacific Gas and Electric, the Keck Foundation, and the various NSF, now CSSI programs. Okay, so that shows a little bit the institutions involved. It's not only on the West Coast, it's worldwide, and multiple institutions there. So what I want to talk about today is how what we're doing can help reduce risk. So how we define risk is by the 3 Ds, so deaths, dollars, and downtimes that come from earthquakes. We start from the hazard. That's really what SCEC focuses on here. You know, the faulting, the shaking can trigger other issues like other cascading hazards like tsunamis, landslides, and so on. But then you multiply, you integrate all over the hazard, over the exposure. Do you have structures that can be damaged, human infrastructure in there? You multiply by the vulnerability. If the structures are really tough, are not going to be damaged, you will have less risk. And you divide that by the resilience, so the capacity of society to recover from those events. So we really focus on hazard. When you compute the risk integral, the hazard has a very large uncertainty. And what we want to do overall is to try to reduce this uncertainty so we can do better risk assessment and make better decisions. So I'm starting with a conclusion. What we want to do is really use risk-informed decisions for design, for retrofit, and all that. So you go after the most vulnerable facilities, hospitals, dams. You know, if you lose water, you're in a bad shape. All those different critical facilities that are vulnerable and that have a high risk, you start retrofitting them, and you go through the cycle and you get better. We also want to focus on research that helps, you know, and reducing that risk. So I'm doing quite a bit of a background here, but I thought it would be more interesting just to get you in the mindset of what we're thinking about. So we want to prioritize research topics also with the ones that may affect most risk. So what we're trying to do is really improve the hazard assessment. Again, there's a lot of uncertainty there. We want to use validated physics-based simulation models to learn about earthquake processes. So anybody can have models, but do they replicate what we see in the world? Validation is not simple, it's tricky, even if we have data. Then we want to take that and reduce the epistemic uncertainty. I'm not going to go into details on that, but really reduce the uncertainty. Epistemic, I see it as there's only one right answer, but we don't know what it is, right? Epistemic uncertainty is trying to get to that. So we want to collect more data. We want to refine our models, validate, check again, see how they perform, and quantify the uncertainty and its range. And then we repeat and improve. And that's the kind of things we're doing at SCEC, for example. So immediate motivation for ground motion simulations. So there's limited recorded data sets. And right now, for really high-end designs, what engineers do is time history analysis. They take seismograms, put them under their buildings, the structures, and so on, and shake it. And then integrate to risk using multiple ground motions. Well, we don't have that much. So it may look a lot here. This is distance and magnitude, the main characteristics that contribute to ground motions. The red box is really what's the most important for hazard for us. So that's for California and other tectonic regions. These earthquakes come from all around the world, but they're in a type of tectonic region similar to California. When we go to the central eastern US, well, we don't have anything. So what are we going to do? We need simulations. And you would think, well, you know, central eastern US, they don't have earthquakes. Well, the largest earthquakes ever known in North America were near New Madrid, in the Mississippi area, and in Quebec, where I'm from. That's why I talk funny. And very large earthquakes. So we're in the realm of very low probabilities, very large consequences, and it's very important that we design for those issues. So today I'm focusing on ground motion simulations. We also do data mining at SCEC. We have projects that try to look for earthquakes in noisy data, more or less like a Shazam for earthquakes. I'm not going to talk about those today. I'm really going to focus on simulations. So what are the ingredients for ground motion simulations? First, you need what we call an earthquake rupture forecast. That's what we know about the faults that are there. Their representation, geometry, their attitude, how they interrelate to each other, and going to transfer eventually stress. And we want to know their long-term rate of earthquakes. So you probably know, if you don't, I'll tell you now, we cannot predict earthquakes, not in the short term and not with a precise location and date. But we're pretty confident over the long-term probabilities of earthquakes reoccurring, you know, so in terms of a few thousand years and so on. So this, we think we have a pretty good idea of what is most likely to happen. So we use these things. And just so you know, when we do earthquake hazard, we also consider off-fault earthquakes. For example, Northridge, that happened in '94, that was the most costly earthquake back then. What happened on the fault that we didn't know was there. So we do account for that when we do our modeling. Then we need 3D models of the geologic structure of the Earth. This is usually obtained by using ambient noise or past earthquake recording. You do an inversion to capture the velocity structure. So the velocity at which shear waves travel through the Earth is really is important for us. So we can refine those models with more data and all that. If you don't know anything about an area, you're going to assume that it's a 1D layer model, and the waves get trapped and reflected and refracted. We know it's not realistic. The Earth is very complex and has large-scale and small-scale heterogeneities in it. So we develop those models. That's something we do at SCEC as well. And we also want to capture the shallow site response. If you remember from Loma Prieta, '89, seeing the freeway collapse, well, that was just exactly at a place where you had rock and suddenly you had very soft bay mud. At that interface, the demands were very different because surface site effects. Then we're going to take those ingredients and we're going to calculate, we're going to model the fault, calculate wave propagation through the medium, and then get our ground motions from there. So it's kind of simplistic view, but these are the main ingredients we need. So I want to show you, this is an old simulation, 2008. Well, you see why I want to use it. I want to show you here, it's going to be a little video here. We see LA's here, San Diego, of course the Bay Area is further up there. The Shakeout Scenario was developed in 2008 as an exercise to try to test our preparedness for earthquakes, but it came out with this nice simulations I'm going to show you. So here's the dashed line is the segment of the San Andreas Fault that's going to rupture in the video. It's going to start from the south near the Salton Sea and propagate to the north. And what I want you to pay attention is that we have in LA and San Bernardino, we have very deep shallow sedimentary basins in which waves get trapped. Same thing near Ventura and Oxnard here. And you will see in this video that the waves get trapped and reverberated. It's kind of stuck in this jello bowl there. So I'm going to start the video. It's accelerated with time, but you'll see the wave front and how the rupture zips through. So an earthquake is not an instant process, obviously. So it propagates like this. The white values are the largest ground motions. But you see the wave front stacking here from what we call directivity. And it's happening, and you see, even though the fault is here, there's a big set of train of waves here that get focused in the LA basin, and that get trapped, and you'll see they remain there, and they're just happy, shaking. So this simulation and similar simulations were really helpful for us globally as a scientific community to learn what's happening in there. You see what we call here a coupling of directivity and basin effects. So here are two snapshots of similar scenarios. What you see, the red, it's the same fault segment pretty much that ruptured. The left is similar to what we just saw. So the very warm values are ground shaking, real large ground shaking, LA's here. Now we take the same fault and we start the rupture at the north and go south. Because of the structure of the earth, suddenly there's almost no shaking in LA, you know? So those things were really important, and this coupling of directivity and basin effects was really important. And now, after that, other people try to model that with empirical, simpler equations. It doesn't quite work because only simulations allow the coupling of these things together. So, shakeout scenario, what did we learn from that, and why did I show you that? It was a very important thing for us as a whole. So there was a main shock, a lot of aftershocks happened, thousands and thousands of landslides would have been triggered from that. 1,600 fire ignitions, somebody's going to talk about fire simulations. Talk about cascading failure, right? You break gas lines, you break water, you cannot, you know, all these things that can happen in cascading failures. I mean, if this happens, there's not going to be water in LA for months because the San Andreas Fault cuts pretty much most of the water supply to LA. So it was in the hundreds of billions of dollars in direct cost and all that. So exercises like that are really important, and it was not the worst case scenario. It's a plausible earthquake. Actually, for LA itself, the worst case scenario would be a 6.5 right underneath LA, right? So location, depending where you're at, makes a big difference. So the exercise's impact, it was the largest emergency response exercise in the US. It was close to 6 million participants. Now you may hear the shakeout exercises every October. Now we have 50 million participants around the world. So it showed that even LA, who is really prepared, was not prepared. I mean, you cannot live with months without water, and so on. So it really helped change how things were thought of, and there was a new task force created in LA, and the Resilience by Design project was now passed as a law to strengthen the water supply, telecommunication, and so on, and non-ductile structures which are dangerous. Anyways, we can have a lot of impact. It takes time. So we're, you know, this was enacted just 3 years ago. So these things are important. So where are we going now with that? So we have done a lot of simulations since then. So within SCEC, we have different ground motion platform simulations. So here are the seismic bands with frequency and period, depending how you like to think. And the earthquake engineering band of interest here, you know, tall buildings, you know, tanks, you know, they respond to very low frequencies. Short buildings, houses, you know, in that range. Stiff structures, nuclear power plants, dams, HPC centers, equipment, hospitals very sensitive to high frequencies. So we do model, we have different platforms that do different things. Our broadband platform uses a 1D layered structure of the Earth because it's fast and quick and all that. And it's mostly deterministic, so the full wave propagation up to 1 Hertz. and the rest is stochastic. It's still physics-based, but it's stochastic process. And it's used for development, production. It runs on clusters, and it can run on your computer, but on clusters we run thousands of simulations at once. CyberShake is the main thing I want to talk about today. It's a really cool platform that does full 3D deterministic wave propagation. This definitely runs only on HPC, and right now it's only running on Blue Waters and Titan. Those are the two resources that can deal with that platform. I'll talk about it in a bit. We have Broadband CyberShake, where we tie in the stochastic process to CyberShake, so we have a broader range of applicability, and that's also something we're continuing to develop. And we have HiF. HiF for us is really a testing platform, development. How do we integrate better physics, validate, make sure the models work, make sense and all that. And we do that more on a one-off, and we test and so on. Once the science is ready, then we can integrate those physical models into CyberShake. So our allocations over time, we started very modestly with almost nothing. And now in 2018, we have about 460 million service units. And of course, we use them all. We go through competitive proposals to get those resources, and we've been successful so far. And as you can see, it takes a lot of people to make that happen. Not only the scientific collaboration within the center, but all those different groups and their resources, both financial and in terms of support. So that's really exciting. We really like this. Okay, Broadband Platform. I mentioned it's an open source distribution. You can download it and try to run your computer. It does broadband. It's a simple source and path. We have a bunch of different codes in it. So you can test, and we cover a little bit of the epistemic uncertainty, different ways of modeling wave propagation. We spent 1.5 years validating the platform, creating it, allowing like unique input, unique output, but all different mechanisms inside. And we published a full special edition on the validation there. We keep on validating, adding new events. So we use recorded events, and we test the methods against them with a suite of metrics. So far, Broadband Platform has been used for large ground motion projects in the US for nuclear power plants, and now it's used in Taiwan, and it helps supplement the empirical models. Let's talk about CyberShake. So PSHA stands for Probabilistic Seismic Hazard Analysis. So again, we're going to start with the same ingredient, right? We have the earthquake rupture forecast. Where are the fault, their magnitudes, their distribution, and their probabilities over time. In general, when it's done for the building code and seismic hazard maps, what people use is ground motion prediction equations. It's just a suite of equations that parameterize earthquakes in a simpler form. And they produce ground motion intensity measures that are used by engineers. But these PSHA results do not allow to have seismograms at the end. So you cannot do those high-end analysis. You don't have recordings for them. So the goal of PSHA is to integrate the sources and the wave propagation, the side effects and all that, and to get a hazard curve. So it's hard to read, but this is basically the annual rate of exceedance. And this shows the ground motion intensity. So as you go to lower probabilities of exceedance, the ground motions get much larger, and the design is much more stringent, or it needs to happen this way. So that's how it's done. What we do with CyberShake, we do it full physics-based. So we take those different faults. Here's an example of a fault surface where you see the slip distribution on that fault. We run tons of them. We combine that with our 3D structure of the Earth, and then we obtain seismograms at every station that we put for the simulation and so on. From that, we obtain hazard curves. So we also have hazard curves, but we have full seismograms for that. We perform disaggregation. Disaggregation here is the percent contribution with distance and magnitude relative to your site. Tells you which fault are most likely to affect your site at different points on the hazard curve. It's really useful for design. And eventually we can produce hazard maps that kind of look like that. So CyberShake is extremely powerful. It was developed over the years, and it's really an exciting tool. So the last study we did is 17.3, so in March of last year, for Central California. Our previous CyberShake domain over the last 10 years or so was always that black box, Southern California. It's the first time we move up north. And so the box was much larger, and now we covered the full the Central California area. And here's an example of a hazard map. So in here, if I was to look at each single event, I would see those large, ground motions depending on the wave propagation and so on. When we do hazard, we integrate over a lot of possibilities, so it gets smoothed over a little bit. But there are variations here that are representative of the basin structure under the Earth, and that's really important. So we did that. Again, we did 2 velocity models for that, 1D. So for us to test, if we don't know anything, we do 1D. Single layered, Earth, and then 3D. We selected 438 sites. We did 1 Hertz simulations, and to produce a hazard curve, we did more than 40,000 earthquake simulations. So it's a pretty big calculation. We used Oak Ridge Titan and NCSA Blue Waters. So here are the stats a little bit, but the make span of 31 days, so lots of time. We used close to 1 million node hours, so 22 million core hours on this. We have complex, complete workflows using Pegasus, Condor, and also Globus to deal with the transfer. The workflows did schedule close to 16,000 jobs to both systems, and we transferred 300 terabytes of data between the 2 systems to make that happen, because we try to optimize, the computation, the post-processing, and all that stuff. From that, we generated 285 million 2-component seismograms. So you remember my chart where there was nothing in the map for the magnitude and distance bin that mattered. And now it's full, if we take that. 43 billion intensity measures, that's usually what people use for doing design. So of course it means nothing if we don't do validation, so we're doing validation of that. So the workflow, again, managed close to a petabyte of data. At the end, our product that people can have access to with help from us for now, until we fully develop the API service for that. It's about 11 terabytes of data. So the normal average researcher cannot even ingest the data to deal with it. So we parse that up and optimize that. So CyberShake 17.3, here's the example. The 1D model looks a lot, that's a hazard map. It looks a lot like if we use those empirical models, it would kind of look like that. The reason the ground motions are larger here, this is the San Andreas again. There's a faults all over. Once we do the 3D, we capture those differences due to basin effects and structures. Thank you. We're going next. So here now we have the full SoCal, Central California. We're going to start study 18.5. So we're about to start Northern California and run CyberShake. It's even larger. This is going to be a monstrous calculation. We have like almost 600 sites on this. But then again, to continue and move on, eventually to have a statewide CyberShake. So again, what's really cool, at each site that we do a computation, we have seismograms for that. So it was the first physics-based PSHA model. It was used as database for machine learning for the earthquake early warning system. It's the leading model in the USGS right now for really make their urban seismic hazard maps more local. And it's a source of the new design maps for LA for tall buildings, consideration in the building code. HIAF project, a few minutes on that, quick. Again, we're trying to push the limits of the physics there while improving the computational efficiency. So we want to add fault roughness, near-fault plasticity, topography, and all those different effects that are important to real earthquakes to model them correctly. Here's an example. If we include plasticity in the near-fault material or in areas where we have deep basins, and I'm going to show you just a quick video here because videos are fun. And on the left, it's linear, and on the right is nonlinear. It's pretty much a similar rupture to what we looked at before. So you'll see the wavefront propagation. The green shows a damage zone, so there's plastic deformation in there. What you see is those little seismograms are going to start to create themselves as the shaking happens. And If we don't consider plasticity, we find that we have much larger ground motions. Look at this seismogram here, and a lot more significant cycles happening. Now what we need to do is really define how much is the correct plasticity, how much do we put in to replicate the real Earth. But this example showed a reduction of about 30% when you use plasticity. So a quick couple notes. You guys are HPC people, so you might be excited about this. We keep on working, optimizing the codes all the time. We have a team dedicated to that. They're mostly located at San Diego supercomputer. We have improved tremendously. The non-linear code has extreme efficiency, and non-linearity requires a lot more work. And if we look at the CyberShake results alone using that code, AWP is what we use, 6.5 speeding in just optimizing the code. That was on the NVIDIA GPUs. We also worked and port that to the Intel Xeon Phi, and we achieved a 2 times speed up over the best we could have on this. Lots of work to update and port the codes to the different systems. That code was used for a large simulation in China, and it did win the Gordon Bell Prize last year, so it was really cool for us because the code was developed by the SCEC people. We're developing new technologies, and that's a new code, finite element, extreme scale, discontinuous Galerkin code. Very, very impressive scaling on Cori. Here we're talking about 38% of peak here. I think it's one of the best performing code they've had on NERSC there. So very exciting, still lots of work to do. Takeaways, so ground motion simulations on HPC are a great learning tool for scientific research. They're already impacting design, improving hazard, and will help us reduce risk. There's continuous development needed, both on the science and computer science front, and collaboration is essential. I mean, you cannot do that with just a few people to really do the best you can. What's next? We want to replace the earthquake rupture forecast with an earthquake simulator. I think somebody's going to talk about long catalogs of fire. We do million-year catalogs of earthquake generation, just earthquake and how the faults, trigger other faults and so on. We want to replace that with the kind of static definition. We want to go to higher frequencies, extend the range of applications again, because that's what we need to be more relevant to society. We want to continue and test and implement additional physics, formally evaluate those uncertainties, and use, again, simple models as benchmark, the 1D, to see how much we do if we do more complex simulations. Do we have a gain there? So, and then we validate, because it's essential. And thank you, and this is really, I'm just presenting for a group here. It's a tremendous group. Thank you very much.
With the number of earthquakes we have in the central United States due to the fracking, I wondered if they can use that model on that, just because it seems like every week there's something, so you could test your models against the infrastructure in the central states.
Yeah, we can test the ground motion itself, not the generation, because it's really linked to a trigger. Right. But yes, absolutely, that's a way to test. But they're very small earthquakes. Right. But yeah, we absolutely, yeah.
Okay.
So, knowing what you know, do you still live in California?
Yes, absolutely, and that's my home. I love it. Yes, I'd rather live there than in Seattle with tsunamis, volcanoes. Too much.
Hi. What is your role for physical simulators?
Physical simulators? Earthquake simulators. So we already are using some of them, but yes, we want to continue using them to replace the static earthquake rupture forecast. We're using them. Definitely. That's another part I didn't really cover, but there's, multiple groups within SCEC doing that.